examples from the practice that I posted online. Both of them had typos, which I think is probably why most people didn't get them correct. But I still feel like they are good examples for us to go through. Just that way, then you have some extra examples of our area between curves. Alright, so the first one that we're going to look at is number 3, which is this one. And it asks us to look at which of the following intervals is equal to the area that is inside the polar graph of 2 cosine, but outside the polar graph of our cosine. So we're looking for this shaded green area. So remember that if I'm looking for the area between 2 stuff, like this is situated. So remember that our formula is A equals 1/2. That's not a good thing. Alpha to beta of R of our outer.
Abby, are you the only one here?
Yeah, Andrew is here,
Minus
but he went to the counselor.
R of our inner.
Okay.
Bye.
Right. Very good with that.
Yes.
Okay. But remember that this one only works if they are actually all of this stuff is between them. Because on number 7, which is what we're gonna look at next, it doesn't quite work that way.
Yeah. But the mini circle is all the way in the big circle.
Correct. So our first thing that we want to do is find our bounds. So we set them equal to each other.
Why? Is we're finding where they are at the origin, like where they're crossing the line.
Correct, which is what we're gonna get. I'm just showing you the process that would work for anything, right? Because remember, sometimes we're not necessarily gonna be given the graph, so we want to just be able to see that it is 0 and pi over 2, what it's gonna be. But so if we are looking for our bounds, then we can just set them equal to each other. So in this case, I would subtract the cosine, and I just get cosine equals 0. Which happens at pi over 2 and 3 pi over 2. Yes, no maybe? Now remember that the other way that we can actually see this, because this is cosine, is technically they sometimes will write it as a negative pi over 2 to pi over 2 instead.
Yeah.
But because we don't like negatives, and also notice that this is symmetric, okay? Instead of going from negative pi over 2 to pi over 2, we can go from 0 to pi over 2 and just double it. Yeah. Again, we don't always have to use the symmetry, but it just makes our lives easier if we go ahead and use the symmetry. Okay? So then we just have to look at our inner and our outer, which our inner is going to be our red circle and our outer is our blue circle. So we get 4 cosine squared of theta minus cosine squared of theta d theta. So then my 1/2 and my 2 go away, so I have 0 to pi over 2. This becomes a 3 cosine squared of theta d theta. And then we can just bring the 3 out to the front. Okay. Now on this one it just asked us for the setup. So we didn't actually have to evaluate it. And like I said, this one had a typo. So it was missing, I think they put it as A, but they forgot to put the 3 on there. So that's what it should have been. So it is A, but there should be a 3 right there. I'm looking at.
What would you do to evaluate that angle?
You would use, remember, our half angle, right? So we would have 3 b times 0 to pi over 2. And then
1 plus cosine of 2 theta over 2.
yes. So like we could rewrite it with our half angle as 1/2 plus 1/2 cosine 2 theta. D theta. And then we can just do a u sub with our
Yeah. Okay.
yeah, that the half angle one is the one that we use probably the most often. Every once in a while we'll use that double angle one, because remember sine of 2 theta equals 2 sine theta cosine theta. But generally if we have something like this we can just do a u sub because I have a sine and a cosine. So we tend to use the half angle the most just because there's not really another way to do that. So. Alright. Then on number 7, it looked like this. The typo here was I don't know what that was supposed to be.
Yeah, I graphed it without the s.
Yeah.
And
So
it made sense. So.
Correct. It was just supposed to be 2 times 1 minus
I
cosine.
remember I got this one wrong. I was sad.
Okay.
Because I thought I did it right.
Gotcha. Now, the biggest difference on this one is that, like, notice that our area in between, like, I don't have one completely inside of the other one. Does that make sense? So, like, technically my blue one is inside of the red one on the right hand side, but then my red one is inside of the blue one on the left hand side. And so we can't do our outer squared minus our inner squared because one is not completely inside the other.
Yeah.
Does that make sense?
Yes.
So what we have to do instead is just like a little bit of like critical thinking. So first off, we do want to find our bounds. So again, we're just going to set those two things equal to each other. So I have 2 times 1 minus cosine theta equals 2. So I can divide both sides by 2. I will also end up with a cosine of theta equals 0. So theta equals pi over 2 and 3 pi over 2. Or, again, we can use our symmetry. So, the thing to notice here, what we want to do is we basically want to cut this in half. Not half, but cut it into parts. Because notice that on the right hand side, this shaded region is just given to me by my blue graph. And then on the left hand side, that region, the shaded region, is just given to me by my circle. Does that make sense? Okay. So, my first, I'm going to look at my the region that's to the right. So, again, I have 1/2. And notice that my top and bottom are symmetric again. So, I'm going to double it and go from 0 to pi over 2. Because, again, that's where that point is going to be. And so, that's where they're going to switch from my cardioid to my circle. Does that make sense? Okay. And then remember that on the inside, it's just gonna be r squared this time. So again, my 1/2 and my 2 go away. So I'm left with a 4 times. Notice if I multiply this out, I get 1 minus 2 cosine theta plus cosine squared of theta. D theta, I forgot what I did there. D theta. So I'm going to go ahead and pull this 4 out just because it makes my life easier. And then we need to do basically the same thing that we talked about before, but with our cosine squared this time. And remember, the only difference between our sine squared and our cosine squared is the sign, S-I-G, and positives and negatives. So we're going to have 1 minus 2 cosine theta plus, again, it's a 1/2 plus 1/2 cosine 2 theta this becomes a 3/2.
And then it's just another U sub.
Correct. So like here, I still have a 4 out here. This is going to be 3/2 theta. This is just going to be minus 2 sine theta. If I do a U sub, I'm just going to end up with an extra 2. So I would divide it. And so we're going to have a 1/4 here instead. And we're evaluating from 0 to pi over 2. Right. So then we're plugging in. So my first one is just going to be pi over 2, which notice is why our answers end up with pi then, minus sine of pi over 2 is
0? Oh, wait, sine of pi over
is
1.
1. Yeah. Because sine starts at 0,
Cosine
0.
is 0.
Correct. So we just get a 2 here. And then if I plug in a pi over 2, my 2's would reduce, so I just have sine of pi, which would also be a 0. Yeah. And then notice that when I'm subtracting, plugging in 0, this is 0, sine of 0 is 0, and then 2 times 0 is still 0, so I just get 0 for everything. So then this ends up being, what do I get? So this would be 3 pi over 4, but my 4's are going to reduce, so I just end up with a 3 pi minus, and then distributing, I get 8. So again, that is like the little like mountain shapes that we have there. That's the area of that part. Then on the left-hand part, you can set up a nice big old integral, or it's a semicircle. Yeah. So I'm just looking at my area. I'm gonna say area L for like the left-hand side. And so this is for. Remember, we're going from pi over 2 to 3 pi over 2 for that one. Again, if we were had to set up an integral or whatever, just important that we remember what our bounds are there. But basically, it's just pi r squared divided by 2. Our r is going to be 2. So we get 2 pi. And then we're adding these two things, right? Because I want all of it. So I just take my first area. And I'm going to add my second area. Which is where we get the 5 pi minus 8. So I think that's the hardest part about our area between stuff is because like for when we just did like normal XY stuff, it's always top minus bottom or left minus right. Yeah. But with our polars, because like sometimes stuff is inside of other stuff, but other times it's not, like we have to kind of treat them individually, or at least look at them to see like which format I want to use. So like if one of the things is completely inside of the other thing, we can do outer minus inner.
Yeah.
Otherwise, there's a good chance that like for part of it, I'm going to be able to use part of one, and for the other part, I'll be able to use a different one. So really the biggest part is then just figuring out where your bounds are. And then also remembering how to reduce using our half angle. Because that comes up a lot.
I did make a flashcard.
Okay.
Started making flashcards.
That's good.